Over 500 million years ago, Earth's oceans were filled with strange alien creatures, the first explosion of complex life. Tonight, we'll travel back to the Cambrian period to see how it all began. If you enjoy this calm journey through deep time, please like, subscribe and share, and tell us in the comments, which Cambrian creature would you want to see alive? Thank you for watching. Now let's begin. The Earth turns under a pale sun that burns weaker than it will in later ages. Its light filters through a thin, shifting sky made of gases that only recently began to favour breathing. Below, oceans stretch without end, broken by low continents that appear as worn shields of stone. The air carries little colour, faintly touched by oxygen, and still dominated by older gases, carbon dioxide, nitrogen, traces of methane. The ground remains largely bare. Winds sweep across coarse sands and lifeless gravel, shaping ridges that glint faintly beneath the daylight. Only the smallest signs of life cling to the margins where sea meets land, thin films of green and brown that spread across moist rock surfaces, colonies of cyanobacteria quietly releasing oxygen into the air. For billions of years, life has been microscopic, an invisible fabric in the water feeding on light and chemical energy. Now, near the dawn of the Cambrian, that quiet endurance begins to shift. The planet has been cooling for long ages after violent thermal cycles that scarred it with glaciers and volcanic plains. The oceans, once suffocating with iron and sulfur, now hold enough free oxygen to change their chemistry and colour. Bands of iron that once precipitated out of anoxic waters are gone. Instead, clear shallows glow green-blue with dissolved minerals. Beneath them, sediments of fine mud gather in patient layers, recording slow rhythms of tide and storm. The continents, still clustered in unfamiliar shapes, carry the memory of older collisions. Laurentia Baltica and Siberia lie near the equator, fringed by shallow seas. The great southern mass of Gondwana stretches toward the poles, its interior dry and barren. Around these edges, warm eparic seas creep inland over low-lying rock, creating broad platforms of light-filled water that will soon cradle the first ecosystems built on animal form. In this still moment before the explosion of complexity, conditions align in silence. The balance of oxygen and carbon sets a threshold where larger bodies can sustain active metabolism. Oceans mix more deeply as currents strengthen under the pull of the moon and the rotation of the Earth. Nutrients released from erosion and submarine vents spread through the shallows, feeding blooms of microscopic algae. The sea surface glitters with floating plankton that build tiny shells from calcium carbonate particles so small they drift like dust. When they die, their remains drift downward, settling into soft mud that thickens into future limestone. Each grain adds a page to the record of change, preserving the chemistry of water, the isotopes of carbon, the faint pulse of life rising toward visibility. Beneath these calm surfaces, unseen networks of microbes continue their work. Stromatolites' layered mounds built by bacterial mats dot the shallows. They trap fine sediment and grow upwards, slowly forming domes and ridges that sway under gentle currents. Around them, mats of filamentous bacteria coat stones, and sand binding loose grains into crusts. They are living textures of colour green where photosynthesis dominates purple and black, where sulfur-eating species thrive in shade. These microbial communities stabilise the seafloor, fix nitrogen, and release gases that circulate into the atmosphere. Though small, they alter the planet profoundly, creating the conditions that will allow animals to breathe, move, and eventually feed upon one another. The light that filters through the Cambrian water creates distinct worlds by depth. Near the surface, sunlight penetrates meters deep, fueling photosynthetic life. Tiny organisms float freely, forming a haze of living matter. Below them, dimmer zones shelter communities that depend on drifting organic rain from above. Further down, oxygen declines, and the seafloor becomes a realm of stillness and decay. These vertical layers structure the ocean long before complex animals take shape within them. In quiet darkness, chemical gradients form rich in hydrogen, sulfide and methane echoing older Earth. It is within these contrasts between light and dark oxygen, and anoxia surface and abyss, that the stage is set for evolution's new experiments. Volcanic activity remains common along spreading ridges. Submarine eruptions release heat and minerals into the water, creating vent fields that shimmer with metal-rich plumes. Around these hot zones, microbial life flourishes in ways that do not rely on sunlight. Chemosynthetic bacteria convert chemical energy from sulfur and iron into organic matter. These early deep-sea ecosystems remain stable and ancient ancestors of life's earliest forms. Their quiet persistence provides a model of energy transformation independent of the sky above. In contrast, the shallower environments will soon become the testing ground for a different experiment, one driven by oxygen light and the mechanics of movement. The atmosphere of the Cambrian dawn would feel heavy and strange to a modern observer. Carbon dioxide levels remain many times higher than in later eras, yet they are declining. The warmth of greenhouse gases prevents the return of the global freezes that ended the Proterozoic. Cloud cover and rainfall vary across wide continents, but much of the planet's surface remains dry. Without plants, there are no roots to break rock, no soils to hold moisture, no trees to cast shade. Wind carries fine particles into the sea, delivering phosphorus and other nutrients that accelerate biological productivity. The exchange between land, air and water grows more dynamic, feeding back into the oceanic oxygen balance that drives animal evolution. The magnetic field of the planet continues to shield its surface from solar radiation, but the young sun emits frequent flares. Aurorae may dance at low latitudes unseen by any eye capable of wonder. The days are shorter than in later ages. The Earth spins faster, completing a rotation in roughly 21 hours. Tides are stronger, and their cycles sculpt the edges of the continental shelves. Each rhythmic rise and fall stirs the sediments, oxygenating them and mixing nutrients into the photic zone. In these shallow environments, bathed in light by day, stirred by tide by night, the first large-bodied multicellular organisms will soon appear. At this point, there are no bones, no shells, and no eyes. The only visible traces of motion come from faint burrows etched into ancient mud preserved today as trace fossils. These sinuous tracks, called treptichnus and planiolites, mark the movement of worm-like creatures that grazed on microbial mats. They do not yet reveal predators or complex interactions, but they record awareness and ability to sense and respond. This subtle behavioral step marks a turning point in life's story, the beginning of movement across the seafloor, the start of active feeding and exploration. The ocean floor becomes not only a surface to live upon, but a landscape to navigate. The chemical signals of this awakening are preserved in rock. Carbon isotopes in Cambrian carbonates show fluctuations that indicate changes in the global carbon cycle, linked to biological expansion. Oxygen isotopes reveal warming trends that stabilize shallow seas. Together, they trace the slow acceleration of biological activity, a rise in complexity from microscopic simplicity to macroscopic pattern. The Earth itself seems to breathe more deeply, exchanging gases between ocean and sky with increasing vigour. The quiet world of the early Cambrian holds a fragile balance. Each factor, like temperature, salinity, oxygen, rest within a narrow range that allows evolution to proceed. The planet has reached a point of chemical and climatic readiness. no single event triggers what will come next. Rather, countless small conditions align. The surface of the world, once ruled entirely by chemistry and chance, stands at the threshold of biology's grand experiment. Soon the oceans will thicken with body shapes and motion. The still water will no longer be silent, but for this moment Earth remains poised in tranquil expectation, its shallow seas luminous with potential, its barren lands waiting untouched beneath a pale sun that climbs higher each day across the Cambrian sky. The atmosphere of the early Cambrian appears transparent and thin when seen from above a faint veil around the turning sphere of Earth. It is not the dense blue that later ages will know, but a paler hue filtered by the chemistry of an evolving planet. For billions of years, gases have shifted in slow sequence volcanic emissions, microbial photosynthesis, and chemical weathering gradually redefining what the sky contains. By this time, oxygen has accumulated to a fraction of modern levels, yet it marks a decisive threshold. The faint but rising presence of oxygen allows energy to flow through living systems in new ways. It permits cells to build structures that require steady respiration, and opens the possibility of motion, complexity, and predation. Invisible to sight, the air becomes the silent architect of life's next expansion. The mix of gases is delicate. Carbon dioxide remains high, feeding warmth into the global climate. Nitrogen still dominates as a stable background gas, inert yet essential in balance. Methane, once abundant, has declined sharply since the oxygenation events of earlier eons. Water vapor moves through the cycle of evaporation and condensation, forming transient clouds that carry moisture between sea and land. There are no forests or meadows to transpire vapor into the air. Rainfall originates almost entirely from the ocean's own breath. When rain falls, it strikes bare rock or microbial crusts, washing dissolved ions into rivers and back to sea. There the nutrients enrich planktonic life, creating faint green stains in the shallows visible from afar. Within this atmosphere, the circulation of air begins to resemble a recognizable pattern. Thermal differences between the equator and poles drive winds that shape weather on a continental scale. Yet the continents themselves are low and flattened, offering little obstacle to air currents. Dust raised from dry interiors drifts across coastal margins, its particles eventually settling into the sea. Every grain carries traces of phosphorus and iron, each a potential nutrient for marine photosynthesizers. Over long spans of time, this steady input supports the foundation of food webs that will soon diversify into the intricate networks of Cambrian life. The sun's output is slightly weaker than in the modern age, but greenhouse gases retain sufficient heat to maintain temperate oceans. Global temperatures likely average between 20 and 30 degrees Celsius, varying with latitude and season. Polar regions are cool but ice-free. The circulation of warm water from equatorial seas toward the poles prevents permanent freezing. Evaporation drives strong hydrologic exchange, increasing precipitation in coastal belts, while leaving continental interiors arid. These gradients shape where marine life thrives. The oxygen that dissolves into the ocean from the air above is highest in the cool, agitated waters near shore, lowest in the stagnant basins of deeper settings. Oxygen is the link between atmosphere and ocean. What the air contains determines what the sea can host. When sunlight passes through the Cambrian atmosphere, its quality differs subtly from modern light. With less ozone to absorb ultraviolet radiation, more energetic wavelengths reach the surface. Microbial mats and early plankton adapt by producing protective pigments. The colours that would be invisible to human eyes, deep violets, greens and amber hues, dominate the upper ocean. In shallows where light penetrates to the seafloor, photosynthetic organisms flourish. Cyanobacteria and green algae form thin carpets that capture solar energy, releasing oxygen bubbles that rise to the surface. These minute bursts accumulate over geological time, feeding the slow rise of atmospheric oxygen that has already transformed the red planet of earlier eras into the blue planet of the Cambrian. Lightning still flashes through storm clouds, igniting nitrogen chemistry in the air. The products of these discharges, nitrates and nitrites, wash into the ocean with rain, providing yet another source of nutrient essential for life. The sky, the rain and the sea are connected in a single continuous system of exchange. Each storm carries invisible cargo that will feed the microscopic architects of future reefs. In this cycle, atmosphere and biosphere grow increasingly intertwined. The air is no longer merely the planet's exhalation. It is part of the metabolism of life itself. The evidence for this ancient atmosphere comes to modern science through subtle traces in stone. Iron oxidation levels in sedimentary rocks show how oxygen penetrated surface environments. Sulfur isotope ratios reveal transitions in atmospheric chemistry, marking the reduction of volcanic gases. These data, measured from samples across continents, show that the Cambrian air was still thin by modern standards, but dynamic its oxygen concentration perhaps 10% of today's. Yet even this modest abundance changed biology forever. With oxygen came the energy to build collagen and muscle, to maintain active circulation, and to evolve nerve systems that required constant metabolic support. It was a quiet revolution written in invisible molecules. At the boundary between air and sea, this new chemistry finds physical expression. Waves carry bubbles downward, increasing the gas exchange that allows oxygen to dissolve into surface waters. When winds strengthen, they churn the photic zone, blending warm and cool layers. The resulting turbulence redistributes nutrients and sustains higher productivity. During calm intervals, thin films of organic material spread across the surface, a sheen that breaks into patches under the weight of raindrops. The world at this time feels transitional, neither fully primitive nor yet familiar. Each breath of wind over the water hints at potential, the unseen preparation for the coming diversification of form. Volcanic outgassing continues to replenish carbon dioxide, maintaining warmth. Ash from eruptions settles through the atmosphere, scattering light and feeding mineral nutrients into the sea. Over millions of years, the balance between volcanic release and biological uptake keeps global temperatures within ranges favourable for life. Carbon moves between air, water and rock through slow reactions of weathering. When rainwater, slightly acidic from dissolved carbon dioxide, meets exposed silicate rock, it leaches calcium and magnesium that flow into the sea to form carbonates. The result is a self-regulating feedback loop as more carbon dioxide dissolves in oceans and precipitates as limestone the atmosphere gradually clears. The transparency of Cambrian skies would reveal stars by night with unusual brilliance. Without vegetation fires or dust from agriculture, the air remains pristine. The moon, closer to Earth than today, exerts strong tidal forces that influence both atmosphere and ocean. Tidal winds pulse through coastal regions, mixing air masses in rhythmic patterns. These cycles may help distribute oxygen globally, preventing stagnation. The interplay of tides, wind and light becomes an invisible machinery, keeping the young biosphere alive. Even with these changes, the atmosphere remains unstable on long timescales. Periodic fluctuations in carbon dioxide and oxygen correspond to shifts in volcanic activity, continental uplift and biological expansion. Each variation leaves a mark in sedimentary rock as changes in colour, mineralogy or isotopic signature. The record shows alternating phases of enrichment and depletion, as if the planet breathes in slow motion. During the early Cambrian, the trend is upward, oxygen, rising diversity following complexity unfolding. From a modern perspective, this world would appear alien yet strangely calm. The air lacks familiar sense of vegetation or soil. It smells of salt and minerals. Winds carry moisture over vast barren plains, unimpeded by forests. Clouds form over the sea and dissipate quickly inland. There are no birds or insects to disturb the silence, only the steady hiss of surf and the occasional rumble of distant storms. Beneath this quiet atmosphere, the oceans darken slightly at depth as organic matter accumulates. Chemical gradients sharpen, setting the stage for evolutionary innovations that will feed upon these contrasts. As the Cambrian continues, atmospheric stability will support a dramatic radiation of life. But in this interval, before trilobites dominate and predators roam, the air remains a gentle regulator, neither stormy nor still, but balanced between warmth and motion. The chemistry of the sky mirrors the state of the biosphere, poised between simplicity and the coming flood of form. Each molecule of oxygen released by a drifting cell is an unseen step toward eyes, limbs, and shells. Each gust of wind carries whispers of a new biological world about to emerge beneath it. The atmosphere, once indifferent, has become alive in function, though not yet in sight. It is the unseen breath of the Cambrian earth, steady, thin, and full of promise. Across the surface of the Cambrian earth, continents drift in slow procession, their shapes unfamiliar to the modern map, yet already guided by the deep currents of plate tectonics. The crust moves upon the mantle in restless fragments, colliding, diverging, and reshaping the oceans that lie between them. Gondwana dominates the southern hemisphere, immense and sprawling, extending from equatorial latitudes toward the polar regions. Its northern shores are bathed in warm, shallow seas, while the southern interior lies dry, with winds eroding exposed rock into dust that drifts across the planet. To the north, Laurentia stands as a separate continent, roughly where future North America will form, tilted near the equator and surrounded by wide continental shelves. Between them, smaller blocks, Baltica, Siberia, and numerous island arcs migrate across open ocean basins that pulse with spreading ridges and subduction zones. This is a world of slow but constant movement, a geology that shapes the distribution of life. The arrangement of continents defines where seas become shallow, where reefs can grow, and where nutrient-rich upwellings stir the surface waters. Much of the Cambrian ocean floor is basaltic plain, but the continental margins host long ribbons of carbonate platforms and muddy deltas. Inland seas extend far into continental interiors, their depth rarely more than a few tens of meters. These empiric seas, warmed by sunlight and refreshed by tidal mixing, provide the perfect cradle for the expansion of multicellular life. In their clear waters, new species will arise and spread, tracing the geography of these shallow basins. The link between plate motion and biology is direct. When continents move, coastlines change, habitats expand or vanish, and ocean currents reorganize, carrying nutrients to different regions. The magnetic record preserved in Cambrian rocks shows how continents wander. Layers of iron-bearing minerals align with Earth's magnetic field as they form, freezing a record of latitude. These paleomagnetic clues reveal that Laurentia and Siberia drift near the tropics, their seas filled with sunlight, while parts of Gondwana linger closer to cooler latitudes. The tilt of the planet's axis, similar to modern values, creates recognizable climatic zones, warm equatorial belts, temperate mid-latitudes, and cold but ice-free poles. Ocean currents connect these zones, circulating heat and dissolved gases. The global conveyor of seawater, though simpler than today's, already acts as a regulating system, smoothing temperature gradients and redistributing chemical energy. The Cambrian Sea itself is unlike any that follows. Its chemistry reflects an Earth still adjusting to oxygenated conditions. Sulfate levels are higher, and calcium concentrations have increased through weathering of continental rocks. These changes favour the precipitation of calcium carbonate, driving the formation of extensive limestones that will later harden into cliffs and mountains. The colour of the sea varies from turquoise in the shallows to deep blue-green offshore. Along coastlines, storms churn mud into plumes that extend for hundreds of kilometres, settling into fine laminated sediments that will one day preserve the outlines of early animals. Every grain, every ripple of sand carries information about wind current and the rhythm of tides that beat against the continent's edges. Geologically, the planet's surface is dynamic. Volcanoes erupt along mid-ocean ridges, releasing gases and creating new crust. Subduction zones recycle oceanic plates beneath continental margins, feeding chains of volcanic islands. In places where plates diverge, rift valleys flood with seawater, forming new basins. These shifting boundaries create a patchwork of environments: shallow lagoons, open shelves, and deep trenches. Each one offers different conditions for life. The organisms that evolve here will learn to exploit the gradients of light, temperature, and chemistry that such variability provides. Over millions of years, tectonic movement and biological innovation will reinforce each other as changing geography drives adaptation and extinction in alternating waves. Weathering on land contributes to the nutrient balance of these oceans. Without vegetation to hold soil, rain and wind erode rock directly. Rivers the sparse and short carry dissolved minerals to the coast. The delivery of phosphorus, iron and trace metals stimulates planktonic blooms, visible from orbit today as faint swirls of green. In the Cambrian, such blooms form along continental margins, feeding microbial mats and filter-feeding animals alike. The result is a gradual enrichment of surface waters where sunlight and nutrients meet. Oxygen levels rise further in these productive zones, while deep basins remain low in oxygen, creating a layered ocean that sustains both aerobic and anaerobic life. Sedimentary patterns reveal that storms are frequent and powerful. With no vegetation to buffer wind waves, build easily across open water, driving periodic turbulence in shallow seas. Tempestites, storm-deposited layers of sand and shell accumulate across the shelves. Between storms, calmer intervals allow mud and carbonate grains to settle in even sheets. This alternation creates rhythmic bedding, a geological heartbeat marking the planet's shifting weather. Within these sediments, the first abundant animal traces appear. Burrows, resting marks, and feeding trails intersect the seafloor, evidence of activity in environments that were once inert. The dynamic interplay between continental motion, climate, and ocean energy defines this new world's texture. The positioning of continents near the equator enhances photosynthetic productivity. Long days of intense sunlight drive the growth of plankton, which in turn releases oxygen as a byproduct. The global carbon cycle intensifies. More carbon dioxide is drawn from the atmosphere into organic matter and carbonate sediments. This feedback continues to stabilize climate, keeping Earth warm but habitable. The accumulation of carbonate platforms along tropical shelves begins to define future geological landmarks. Thick successions of limestone formed grain by grain from the remains of microorganisms create vast banks that will endure for 500 million years. In some regions, evaporitic basins form where restricted circulation and high evaporation concentrate salts. These zones yield gypsum and halite deposits, evidence that climate varies across the Cambrian world from humid to arid. The absence of complex plants allows wide temperature swings between day and night, further influencing weathering rates. dust lifted from deserts reaches distant oceans, adding iron to the surface layer and sustaining productivity. The coupling of geological and biological processes tightens as Earth's surface matures into a fully interactive system. From a global perspective, the Earth of the Cambrian appears balanced yet restless. Its continents drift slowly, but their cumulative effect is profound. Over tens of millions of years, ocean basins open and close, reshaping circulation and climate. This constant renewal of geography creates opportunities for isolation and specialization among emerging species. Life will diversify not in uniformity, but in the mosaic created by plate motion. Each shallow sea becomes a laboratory of evolution, each isolated shelf a stage for unique ecosystems. The growth of reefs along continental margins marks a turning point in environmental structure. Simple sponge and archaeocyatid communities begin to cluster into frameworks that modify currents and light. These early reef systems depend on clear oxygenated water, which the stable continental configuration provides. Around them, microbial mats persist, bridging the old world of microscopic life with the new one of visible form. Together they create habitats of increasing complexity, where niches multiply and competition begins. The drifting continents have by their arrangement sculpted the first great marine landscapes. Seen from space, the Cambrian Earth would shimmer with shallow turquoise seas encircling ochre continents. The boundaries between land and water are blurred with countless archipelagos and inland seas reflecting sunlight. Cloud patterns trace the motion of air currents driven by warm equatorial heating and cooler polar outflow. The planet's rotation and tides create continual movement, and with it the potential for mixing life and chemistry on a planetary scale. The continents in motion do more than rearrange geography. They set the stage for biological expansion, establishing gradients, boundaries, and connections that define the early marine world. As this age unfolds, these shifting plates will continue to sculpt the geography of evolution. The quiet interplay of mantle and crust dictates where the next explosions of biodiversity will occur, where reefs will rise, and where sediments will preserve the delicate remains of the coming creatures. The Cambrian world, with its continents adrift and oceans in bloom, becomes a living system shaped as much by stone as by cell, by motion as by metabolism. It is here that Earth achieves a rare harmony, a geological pulse synchronized with the slow but steady rhythm of life's awakening. Sunlight spreads across the surface of the Cambrian Ocean, glancing off the rippled shallows and diffusing downward through layers of water that grow colder and darker with depth. The sea is the dominant landscape of this world, an expanse so vast that it erases the distinction between continents. It is here within the gradients of light and pressure that life finds its structure. From the glittering skin of waves to the silent mud of the abyss, the ocean is stratified into zones defined by light's reach. Near the surface lies the photic realm, where solar energy fuels photosynthesis and shapes all higher metabolism. Below it extends the twilight region, where light fades to dimness and sight becomes uncertain. Still deeper lies the midnight zone, where only chemical reactions and slow currents sustain life. Each layer holds a specific chemistry, temperature, and rhythm, forming a vertical ecology that underpins the entire Cambrian biosphere. In the uppermost meters of water, sunlight is bright enough to sustain dense blooms of plankton. Microscopic algae and cyanobacteria drift freely, converting light into organic matter and releasing oxygen into the surrounding water. Their presence forms a faint green tint when viewed from above the colour of living carbon suspended in motion. Small heterotrophic organisms graze on them, creating the earliest planktonic food webs. As these organisms die, their remains sink, decomposing as they fall and enriching deeper layers with nutrients. This continuous rain of organic debris links the zones of the ocean, ensuring that the energy captured at the surface trickles downward through invisible pathways. Currents generated by wind and tides keep the surface waters in constant motion. In equatorial regions, the trade winds drive broad gyres, circular systems that concentrate plankton and maintain steady temperatures. In higher latitudes, cold water wells upward from the depths, carrying with it dissolved minerals that fertilize the surface zone. These upwellings, though unseen, are vital engines of productivity. They replenish the photic layer and sustain the delicate balance between oxygenation and decay. Where such currents meet continental margins, nutrients mix with sunlight, producing regions of exceptional biological growth, bright patches of life in a planet-wide sea. As one descends below the surface, the colour of light shifts. Reds and yellows vanish first, leaving a dim palette of blue-green hues. The intensity drops exponentially. By 100 meters depth, only a small fraction of daylight remains. Organisms adapted to this zone develop sensitivity to faint illumination, responding to subtle changes in brightness rather than colour. Some possess light-sensitive patches or simple eye spots, precursors to the complex eyes that will evolve later in the Cambrian. These adaptations allow them to detect the direction of a light guiding movement toward the surface or away from predators. Motion and perception begin to intertwine, shaping behaviour in ways that will transform marine ecosystems. The temperature profile of the ocean follows the light. Surface waters warmed by the sun are buoyant and oxygen-rich. Below lies the thermocline, a zone of rapid cooling that forms a physical barrier between warm and cold layers. This stratification limits vertical mixing, preserving chemical contrast that define different habitats. Above the thermocline, photosynthesis dominates. Below it, respiration and decomposition prevail. In this lower region, oxygen becomes scarce, and bacteria that thrive in low oxygen conditions proliferate. Sulfate-reducing microbes generate hydrogen sulfide, giving the water a faint chemical odour and creating black sulfur-rich sediments on the seafloor. These environments, though hostile to most organisms, support specialized communities that continue ancient microbial traditions stretching back billions of years. The clarity of Cambrian water varies regionally. In open ocean basins, low sediment input allows light to penetrate deeply, creating vast transparent realms where plankton float in sparse but steady numbers. Near continental shelves, runoff and storms cloud the water with suspended particles. Here, light attenuates rapidly, and the seafloor lies in perpetual dimness even at shallow depth. Despite reduced visibility, these environments are rich in nutrients, sustaining dense microbial mats and burrowing organisms. Storms periodically disturb the seafloor, resuspending sediment and oxygenating it. When calm returns, new layers of fine mud settle, trapping organic matter that will one day form shale. Over time, this alternation of disturbance and stillness records the interplay between weather and depth. Sound travels easily through the Cambrian Ocean. With no coral reefs or modern fish to create noise, the soundscape is dominated by natural phenomena. The crackle of volcanic vents, the grinding of submarine landslides, the hiss of sand grains rolling in waves. For the simple organisms of the time, vibration replaces sound as a sensory cue. Burrowers detect tremors through the sediment. Swimmers respond to turbulence and flow. The physics of water, its density, viscosity and pressure, determines every interaction. It slows motion, magnifies resistance, and makes buoyancy a powerful force. These properties allow fragile creatures to float effortlessly, expanding the range of possible body forms that can exist without the need for rigid support. Light defines not only vision but also chemistry. The absorption of solar energy warms the surface, driving evaporation and atmospheric circulation. In the shallows, ultraviolet radiation interacts with dissolved organic matter, breaking molecules apart and releasing nutrients. Near hydrothermal vents, where sunlight never reaches chemical gradients, take its place as the source of energy. The coexistence of these two modes, photosynthetic and chemosynthetic, makes the ocean a dual system of life powered by both sky and crust. It is within this spectrum of light and darkness that evolution finds room to experiment. On the seafloor, the texture of the environment varies with depth. In the bright shallows, ripples of sand shift daily under waves. Small burrows crisscross the substrate, and microbial films bind the grains into soft mats. At intermediate depths where storm energy fades, muds dominate. Here, organic matter accumulates faster than it decays, producing dark sediments that record the chemistry of the water above. In deeper settings, beyond the reach of light, fine clays settle continuously, forming layers that may persist unchanged for millennia. These sediments, compressed over time, will become the pages of the Cambrian record, an archive of shifting depths and colours. Reefs begin to rise within these illuminated zones. Built by sponge-like organisms and microbial partners, they form irregular mounds that alter local currents. Light penetrates their porous frameworks, creating microhabitats of shade and sun. These structures provide shelter and feeding surfaces for other organisms, promoting ecological complexity. The relationship between light and architecture begins here. Biological structures modify the way light moves through water, and in doing so they reshape the patterns of life itself. Far offshore in deeper basins, the darkness is nearly total. Yet even here, life persists. Chemotrophic bacteria form thin films on rocks near hydrothermal springs, converting chemical energy into organic matter. Tube-like worms and small arthropods graze upon them. The contrast between these dark ecosystems and the luminous shallows defines the boundaries of the Cambrian biosphere. It is a planet of gradients rather than uniformity, where each layer of depth represents a distinct world. Viewed as a whole, the Cambrian Sea is a continuum of light, fading into shadow warmth, giving way to cold oxygen, yielding to stillness. The structure of this ocean creates the framework for ecological diversity. Every species that will arise must find its place along these axes of illumination and depth. The interplay of sunlight, water clarity, and seafloor texture becomes the organizing principle of early marine life. Light does more than reveal the world, it sculpts it, drawing invisible lines between survival and absence. Beneath the ancient sun, the Cambrian seascape unfolds as a gradient of color and energy, a living prism through which evolution will soon pass, refracting into forms that no world before has seen. Across the Cambrian world, every grain of sand and every flake of mud becomes a witness to transformation. Sediments are the planet's quiet scribes, layering the story of change grain by grain. As waves stir the edges of continents and rivers discharge their burden of minerals, new surfaces are written each day onto the seafloor. These layers record more than motion, they hold the chemical and biological traces of life's awakening. The muds of shallow shelves, the sands of storm-beaten coastlines, and the carbonates of calm lagoons all preserve different aspects of a single unfolding pattern, the expansion of complex life across the world's seas. In the broad eparic seas that flood continental interiors, deposition occurs with a slow regularity that belies the scale of the forces involved. Fine particles suspended in water settle, gradually building laminae so thin that each may represent only days or weeks of accumulation. Over time, thousands of such layers pile atop one another, forming thick sequences of shale and limestone. The rhythm of tides, storms, and seasonal currents leaves subtle variations in grain size and composition. Each change in texture or colour marks a shift in environment, perhaps a storm surge, a brief exposure to air, or the migration of a delta channel. These patterns form the heartbeat of the Cambrian Ocean, preserving the tempo of its quiet revolutions. Storms are among the most powerful agents shaping these sediments. When winds rise across shallow seas, waves penetrate to the seabed, lifting sand and shell into suspension. The turbulence redistributes material across wide areas, spreading coarse layers that rest sharply atop finer ones. As the energy fades, the heaviest grains fall first, followed by lighter silt, and finally by the fine rain of clay. This sorting creates graded bedding, a signature of ancient tempests now visible in cliffs and outcrops. Between such events, calmer intervals allow delicate lamination to resume. The alternation of violence and stillness captures the dual nature of the Cambrian world, a place of gentle continuity punctuated by moments of sudden force. In regions where carbonate platforms dominate, the record takes a different form. Here the sediments are born not from erosion of land, but from the accumulation of skeletal material and chemical precipitation. Calcium carbonate dissolved in seawater crystallizes around fragments of shell and microbial film, forming ooids, tiny spheres that roll with currents like microscopic pearls. These grains gather into vast shoals that migrate with waves, creating cross-bedded limestones that speak of constant motion. In quieter lagoons, microbial mats stabilize sediments, allowing fine mud to settle undisturbed. Over time, these zones produce thick carbonate sequences that preserve the faint impressions of soft-bodied organisms. Mudstones, by contrast, capture the subtler rhythms of the Cambrian Sea. They form in low-energy environments where suspended particles drift down slowly from the water column. Within these soft deposits, early burrowing animals leave traces of their movement, sinuous tunnels, branching galleries, and surface grazes etched into the mud. Such trace fossils, ichnofossils, are often more abundant than the bodies of the creatures themselves. They reveal behavior rather than anatomy, showing that organisms are now interacting actively with the sediment rather than merely existing upon it. The substrate becomes alive, turned over by feeding movement and dwelling. In geological terms, this transformation is known as the agronomic revolution, the moment when life begins to reshape the fabric of the seafloor. Chemical signatures within these sediments tell the parallel story of atmospheric and oceanic change. The ratio of carbon isotopes fluctuates, reflecting the balance between organic productivity and decomposition. Positive excursions mark periods when photosynthesis draws carbon dioxide from the ocean, enriching the remaining dissolved carbon in heavier isotopes. Negative shifts indicate the burial of organic matter, or the release of carbon from volcanic or tectonic events. These variations, captured in carbonate rocks across the globe, form synchronized patterns that allow scientists to correlate distant regions. Through them, the chemical pulse of the planet can be read across continents. Iron formations, though no longer dominant as in earlier eras, still appear locally. They indicate transient episodes when oxygen levels in the ocean dipped low enough to permit the transport of dissolved iron, later oxidized and precipitated as reddish beds. These layers contrast sharply with surrounding grey shales and pale limestones, visual reminders of a world still finding balance between anoxic and oxygenated states. The persistence of such contrasts ensures that life continues to evolve in gradients, adapting to environments that shift from favourable to hostile over short distances. The preservation of organic matter in Cambrian sediments depends on oxygen. In well-ventilated shallows, decomposition is rapid and little carbon is retained. In deeper, stagnant basins where bottom waters lack oxygen, dead plankton and animal remains accumulate with minimal decay. The resulting black shales, rich in carbon, form both an energy reservoir and a detailed record of ancient ecosystems. Within them, soft tissues occasionally escape destruction, leaving behind the carbonaceous films that define exceptional fossil sites. Such conditions are rare, but when they occur, they capture life in exquisite detail. The shape of appendages, the texture of skin, the fine branching of gills. These deposits, known as Lagerstätten, will later reveal the diversity and delicacy of Cambrian organisms in a way ordinary sediments cannot. The colour of Cambrian rocks mirrors their environment of origin. Red beds mark oxidized continental surfaces. Green and grey shales reflect marine settings with moderate oxygen. Black layers denote stagnation and organic enrichment. Even without fossils, these hues tell the story of the ocean's chemistry and the air above it. The alternation of colours within a single sequence records the interplay of climate, sea level, and biological productivity. When sea level rises, anoxic conditions spread. When it falls, oxygen returns to the seafloor. These cycles create a stratigraphic rhythm that echoes the slow breathing of the planet. Mineralogical details add further insight. Tiny crystals of pyrite iron sulfide form when bacteria reduce sulfate in oxygen-poor conditions. Their framboidal clusters sparkle under the microscope, evidence of microbial metabolism locked in stone. Glauconite, a greenish clay mineral, forms in quiet marine settings where sedimentation is slow. Its presence in Cambrian strata indicates periods of stability when the sea remained shallow but undisturbed for thousands of years. Each mineral in its own way is a proxy for environmental process, a coded message from a vanished sea. As sediment accumulates, compaction and cementation transform it into rock. Pore water carrying dissolved minerals moves through the layers, precipitating new crystals that bind grains together. The original textures are preserved, but the material becomes durable, capable of surviving the pressures of burial and uplift. In time, tectonic forces will raise these strata into mountains, exposing them to weathering once more. The cycle of erosion and deposition continues endlessly, yet within each repetition the record of life remains. The Cambrian sediments thus form the first global chronicle of complex ecosystems, a durable memory inscribed across the crust. Viewed collectively, these layers represent more than geological accumulation. They are the physical trace of a biological revolution recorded in stone. Every burrow and ripple, every change in grain size reflects the growing influence of life upon the planet's surface. The sea floor that was once inert now responds to biology, its chemistry altered by respiration and decay, its texture shaped by movement and feeding. The Earth begins to record not only its physical processes, but its living ones. The story of the Cambrian is written not in grand upheavals, but in fine sediment, settling through silent water, preserving the faintest gestures of creatures just learning to inhabit the solid world beneath them. Along the warm continental margins of the Cambrian world, the sea becomes an architectural workshop. Here in shallow, sunlit waters, the first complex reefs begin to rise. Unlike the coral-built structures of later ages, these early reefs are formed by sponges, archaeocyathids, and microbial communities that collaborate in slow-layered growth. They appear as irregular mounds or branching frameworks anchored to the seafloor, built grain by grain through the accumulation of carbonate skeletons. Each reef begins as a small patch of stability and elevated surface, where currents flow more freely and sediment does not easily settle. Over generations, these patches expand as living organisms grow upon the remains of their predecessors, cementing fragments into rock. The result is a fragile but persistent structure that modifies its surroundings and creates new ecological space. The conditions along these Cambrian shelves are ideal for such construction. The seas are shallow, clear and saturated with calcium carbonate. Warm temperatures and steady sunlight maintain high productivity. Gentle currents bring oxygen and nutrients, while periodic storms refresh the water column without destroying the structures themselves. In these environments, sponges dominate. Their porous bodies filter seawater, continuously extracting food particles and strengthening the surrounding chemistry by cycling carbon and oxygen. The archaeocyathids, an extinct group of cup-shaped organisms related to sponges, join them as prolific reef builders. Their calcareous skeletons form rigid frameworks with open chambers that allow water to circulate through the colony. Together they produce layered limestone masses that stretch for kilometers along ancient coastlines. At the scale of the seafloor, a Cambrian reef resembles a miniature city. Its surface undulates with towers, hollows and overhangs. Open channels between growing mounds act as thoroughfares for drifting plankton and sediment. Microbial mats spread across surfaces, binding loose grains into films that stabilize the structure. Around the edges, smaller creatures find refuge, worm-like burrowers, early arthropods and mollusk-like grazers. These inhabitants feed on detritus and bacterial films, forming the earliest known examples of reef-associated communities. The reef itself is both habitat and engineer. By changing local flow, it concentrates food, increases oxygen exchange, and provides shelter from waves. In the Cambrian Ocean, this new form of environmental complexity marks a turning point in the relationship between life and landscape. The texture of these ancient reefs preserved in limestone today reveals a complex interplay of biology and chemistry. Some layers consist of solid archaeocyatid skeletons fused by lime mud. Others contain fragments reworked by currents. Cavities within the structure are filled with later sediment, sometimes containing fossils of organisms that lived after the reef builders died. The vertical succession of growth, collapse and recolonization demonstrates that these reefs were dynamic ecosystems constantly rebuilt by succeeding generations. Geochemical analyses of such limestone show alternating cycles of oxygenation and reduced conditions within the reef's interior, suggesting that the flow of water through the structure was strong enough to sustain aerobic organisms but slow enough to preserve pockets of anoxia, where sulfate-reducing bacteria thrived. In many Cambrian formations, these reefs are surrounded by extensive carbonate platforms. Beyond the reef crest lies a broad lagoon protected from waves and filled with fine sediments. Here, microbial mats flourish their layered surfaces, recording daily cycles of photosynthesis and respiration. At night, carbon dioxide from decomposition dissolves into the water, promoting the precipitation of calcium carbonate. By day, photosynthesis removes carbon dioxide, favoring the formation of oxygen-rich layers. Over long intervals, this alternation produces rhythmic lamination known as stromatolitic texture. Each lamina is a thin sheet of life's residue, representing a moment when microbes stabilized sediment and built new substrate for further growth. These structures, while simple, are enduring, persisting, even as animal life becomes more active around them. The reef environment also influences sedimentation across adjacent shelves. As waves break against reef walls, energy dissipates, allowing fine particles to settle in sheltered zones. The result is a gradient of grain size radiating from the reef. Outward coarse debris close to the structure, finer muds further away. Storms periodically disrupt this pattern, washing carbonate sand back into the lagoon or out to deeper water. When calm returns, the pattern re-establishes itself layer upon layer. These deposits later form the massive carbonate successions that define Cambrian stratigraphy worldwide. In them, the traces of life's first builders are preserved not only as fossils, but as entire landscapes encoded in stone. Reef systems also play a role in regulating seawater chemistry. By extracting calcium and carbonate ions to build skeletons, reef organisms draw down dissolved carbon dioxide. This process links biological activity to the global carbon cycle. As reefs expand, they act as sinks for carbon-stabilizing atmospheric levels and helping maintain a warm but steady climate. Conversely, when reefs decline, weathering and volcanic activity return carbon dioxide to the atmosphere. The balance between these processes is delicate, and it drives subtle fluctuations in temperature and ocean chemistry that echo through the Cambrian record. Evidence from modern analysis of isotopes in Cambrian limestones indicates that reefs influence local oxygen levels as well. Water circulating through porous frameworks absorbed oxygen from photosynthesis and redistributed it to deeper zones. This created microenvironments that supported aerobic respiration in organisms living below the photic zone. In effect, reefs extended the reach of oxygen into the ocean, helping to expand habitable space. The evolution of reef building thus represents both a biological and chemical innovation, a feedback loop in which life reshapes its own environmental boundaries. Despite their importance, Cambrian reefs are fragile. They collapse easily under stress, and changes in sea level or sediment influx can smother them. Yet their vulnerability contributes to their legacy, for when they fail, they release material that seeds new growth elsewhere. Fragments of archaeocyatid skeletons and sponge spicules drift with currents, colonizing new substrates and initiating fresh cycles of construction. This dispersal ensures that reefs reappear across vast regions from what is now Australia and Antarctica to Siberia and North America. Their distribution mirrors the map of Cambrian continents, tracing belts of warmth and stability that circle the equator. Viewed in cross-section, a Cambrian reef tells a quiet story of persistence. At its base lie microbial mats, above them the layered frameworks of archaeocyathids, and within them the infill of lime mud and shell debris. Each layer speaks of time measured not in moments but in millennia. Growth rates are slow, perhaps only a few millimeters per year, yet over millions of years these structures rise tens of meters high. They are monuments of accumulation, the earliest large-scale expressions of collective biological engineering on Earth. Over time, many of these reefs are buried by sediment compacted and transformed into limestone masses that will later be exposed in mountain ranges. When uplift and erosion reveal them again, their forms appear frozen, but intricate honeycombs of calcite preserving the architecture of a vanished world. To the eye, they resemble coral reefs, yet their builders are long extinct. Still, the principle they established endures life, modifying its own environment through construction, creating diversity through structure. The Cambrian reefs are the first scaffolds of ecological complexity, the foundations upon which later marine ecosystems will stand. In the still clear waters of that ancient time, these fragile cities of stone shimmered beneath the light, silent and enduring, as the seas continued their slow revolution around them. The Cambrian seas grow busy. Across broad shelves and quiet lagoons, patterns of feeding movement and exchange weave together into the earliest recognizable ecosystems. For the first time, life is no longer scattered in isolated forms, but arranged in networks of dependence. Every grain of sediment, every pocket of oxygen, every drifting particle of plankton participates in an emerging web of energy that connects surface light to the dark sea floor. The ocean is no longer a silent reservoir of chemistry. It has become a living system in motion. In the shallow photic zones, the foundation of this system is microscopic. Cyanobacteria and algae form the base of the food chain, floating in countless numbers near the sunlit surface. Their photosynthesis releases oxygen, sustaining other organisms and slowly altering seawater chemistry. These tiny cells reproduce rapidly, and their remains rain constantly onto the seabed, forming a fine organic snow that feeds creatures below. Each patch of water functions as a miniature factory of carbon, transforming sunlight into matter that can move through mouths and guts, rather than through chemistry alone. On the seafloor, a different rhythm dominates. Here, detritus from above mixes with sediment, creating a fertile film where microbial mats spread. Early grazers crawl across these mats, scraping the surface with flexible mouthparts. Others burrow beneath, feeding on decomposing organic material. Their motion churns the upper layers of sediment, introducing oxygen into what was once an anoxic zone. This biological stirring, called bioturbation, changes the chemistry of the seabed and allows new species to thrive. It marks a fundamental transition. The seafloor ceases to be static and becomes dynamic, maintained by the organisms that inhabit it. Among these grazers and burrowers are many of the first bilaterians organisms with symmetrical bodies and directional movement. They include early annelid-like worms, priapulids, and small arthropods. Each represents an experiment in locomotion and feeding strategy. Some move through the sediment like threads, others plough across it on jointed limbs. They sense their surroundings through touch and chemical cues, responding to gradients of food and oxygen. In these motions lie the beginnings of behaviour of interaction between organism and environment. The sediment becomes a record of their passage, patterned with feeding traces and resting marks that endure long after their bodies decay. Above the substrate suspended in the water column, planktonic life diversifies. Tiny crustacean-like forms drift, with the currents filtering bacteria and algae from the water. Gelatinous creatures propel themselves gently through the upper layers, capturing food with tentacles. These early drifters occupy a world defined by light and motion, their delicate bodies almost transparent. They are the intermediaries between sunlight and the dark benthic realm below, transferring energy downward through their death and waste. For every organism that floats or swims, countless others depend upon its descent. Predation begins to reshape this system. Where once life consisted mainly of passive feeders and decomposers, now pursuit and defense emerge. Small arthropods develop hardened exoskeletons for protection, while others evolve sensory organs capable of detecting movement and light. This change introduces hierarchy into the ecosystem, the hunter and the hunted. The simple recycling of detritus gives way to direct transfer of energy through feeding. The presence of predators accelerates adaptation, favouring speed armour and awareness. What was once a stable microbial world becomes a landscape of shifting strategies. Still, cooperation persists in quieter forms. Sponge colonies filter the water, removing suspended particles and clarifying the sea. In doing so, they enhance photosynthesis for nearby algae and maintain oxygen flow for benthic animals. Microbes live symbiotically within their tissues, exchanging nutrients and stabilizing their skeletons. Early reefs built by these consortia become hubs of biodiversity. Around them gather grazers, scavengers, and swimmers, all drawn by the shelter and food the structures provide. Each reef functions as a miniature world within the broader ocean, self-sustaining yet linked to the greater cycles of sediment and current. Energy moves through this web not only as food but as chemistry. The respiration of animals releases carbon dioxide that returns to the surface and enters the atmosphere. Decomposition in the mud regenerates nutrients that feed the plankton above. The ocean circulates these materials endlessly, driven by temperature density and the rotation of the planet. This steady recycling keeps ecosystems in balance. There are no forests, no soils, no rivers rich in organic matter, only the sea itself endlessly turning and renewing. Geological evidence preserves this transformation with subtle precision. Sediments once sterile now teem with trace fossils, their density increasing sharply in the early Cambrian. Oxygen isotopes indicate improved ventilation of shallow seas, a sign of biological mixing. Layers of limestone rich in skeletal debris attest to the growing abundance of organisms with hard parts. These rocks form the foundation of the fossil record, the first extensive archive of complex life. In them, the structure of ecosystems can be inferred even when the creatures themselves are gone. The expansion of these networks is not uniform. Some regions remain barren due to low oxygen or excess sedimentation, while others bloom with productivity. Along the margins of continents, nutrient influx from erosion stimulates dense communities. In deeper basins, life persists near hydrothermal vents, where chemical energy replaces light. Each environment offers a variation on the same theme: energy capture, transfer and recycling through living matter. The unity of process across diversity of form defines what it means to be an ecosystem. Over millions of years, these interactions increase the planet's overall biological complexity. The seafloor becomes zoned according to depth, light and substrate. Epifaunal creatures live upon the surface, endobenthic ones within it, and nectonic swimmers above. Each zone connects to the others through feeding and decay. Energy that begins with photosynthesis at the surface may pass through half a dozen organisms before returning to chemistry at the bottom. The ocean has learned to reuse its own substance, and in doing so it achieves stability. The Cambrian ecosystem is still fragile, vulnerable to environmental shifts. A change in oxygen concentration or sea level can erase entire communities. Yet its resilience grows as species diversify. The presence of multiple feeding types, grazers filter, feeders, scavengers and predators, creates redundancy that buffers against collapse. When one group declines, another fills its place. This emergent balance represents one of evolution's quiet triumphs, self-sustaining complexity born from countless small interactions. In the stillness of ancient seas, the first ecosystems reach equilibrium. The water above glows faintly with suspended life. The sediment below is threaded with burrows. Between them circulates a continuous exchange of matter and energy. The planet once ruled by chemistry alone now breathes through biology. Every reef, every mudflat, every drifting particle participates in a cycle that will persist for hundreds of millions of years. From this point onward, Earth is not merely inhabited, it is organized. The structure of the living world has emerged, woven through salt water and sunlight, its rhythm set by the turning of the tides and the slow heartbeat of the Cambrian Ocean. Across the Cambrian seafloor, hard shells begin to gleam beneath the filtered sunlight. Among the sediments and reefs, trilobites appear in astonishing numbers. Their jointed bodies, segmented armor, and compound eyes mark them as a new kind of creature, one that will dominate the marine world for tens of millions of years. Trilobites are arthropods, part of a lineage that has mastered mobility protection and sensory awareness. In their arrival, evolution reveals a new strategy: the use of a mineralized exoskeleton not only for defense, but as a framework for locomotion. Each segment of the trilobite's body moves with precision, guided by coordinated muscles and flexible joints. This mechanical design allows them to walk, burrow, and swim with remarkable control. They represent a leap in anatomy that transforms the rhythm of the Cambrian seas. The earliest trilobites are small, only a few centimeters long, their form simple but efficient, Over time, they diversify into hundreds of species adapting to every possible environment, from shallow tidal flats to deeper offshore slopes. Their exoskeletons, composed of calcite and chitin, fossilize easily, leaving an abundant record that reveals both individual behavior and evolutionary trend. Some trilobites develop broad, flat bodies suited for gliding over soft mud, while others grow spines for protection or streamlining. Their segmented design allows near limitless variation. Each species is a modular experiment in adaptation. The trilobite eye, one of the earliest known in the fossil record, is a compound organ built from tiny calcite lenses. With vision comes awareness of distance and direction, enabling navigation and escape. The seafloor, once governed by touch and chemical sensing, becomes a place illuminated by perception. Trilobites feed in diverse ways. Many are deposit feeders, ploughing through sediment and consuming organic detritus. Others act as filter feeders, sweeping particles from the water with delicate appendages. A few more specialized forms become predators or scavengers, using spiny limbs to grasp prey. These roles integrate trilobites into every level of the food web. Their constant activity stirs the seafloor, oxygenating it and redistributing nutrients. In this way, they become ecological engineers, shaping the very environment that sustains them. Their molted shells accumulate as drifts of fragments across the seabed, creating new substrates for microbial growth. In death, as in life, they continue to influence the chemistry of the ocean floor. The distribution of trilobites mirrors the geography of the Cambrian continents. Distinct species radiate from separate regions, Laurentian, Gondwan and Siberian, each evolving independently in its own shallow seas. When continents move or sea levels shift, populations mix and new forms appear. Paleontologists use these patterns to trace ancient coastlines and reconstruct the movement of tectonic plates. The global spread of trilobites thus provides a biological map of the planet's shifting surface. Their fossils, preserved in fine-grained shales and limestones, record more than anatomy. They record geography, climate and time. Beyond trilobites, the broader arthropod lineage diversifies rapidly. Early crustacean-like forms swim through open water, their antennae steering them through plankton-rich currents. On the seafloor, smaller relatives creep between grains of sand, filtering detritus or scavenging. The arthropod body plan, jointed limbs, segmented torso, hardened cuticle proves infinitely adaptable. It allows both rigidity and flexibility, protection and movement. This design becomes one of evolution's most successful templates, repeated across millions of species through deep time. Even in the Cambrian, the groundwork for future crabs, insects and spiders already exists in principle. Among the more enigmatic Cambrian arthropods are creatures such as Anomalocaris, a swimmer of impressive size and grace. Its body undulates with rhythmic precision, propelling it through the water as it hunts smaller prey. Paired appendages at the front act as grasping arms lined with spines that funnel victims toward a circular mouth. Its compound eyes, mounted on stalks, provide vision unmatched in the early ocean. Though once mistaken for separate organisms, the complete fossil reveals a predator capable of complex movement and strategy. Anomalocaris exemplifies the new ecological order emerging from arthropod innovation: active pursuit, sensory integration, and control of space through movement. Not all arthropods are large or predatory. Many occupy the quiet margins of the sea, burrowing into soft sediment or clinging to microbial mats. Their exoskeletons form intricate patterns of ridges and nodes that strengthen their bodies against pressure. Some display enrollment behavior, curling into tight balls when threatened, an instinctive defense that persists in modern relatives like pill bugs and horseshoe crabs. Others possess broad spines that deter predators or anchor them against currents. These physical variations reflect the diversity of ecological roles arthropods assume within the Cambrian ecosystem. Trilobite reproduction and development remain inferred from fossils, but show signs of life cycles already complex. Tiny larval forms known as protospids suggest planktonic stages that drift before settling to the seafloor. Such dispersal ensures genetic exchange across wide distances, promoting speciation and resilience. As they grow, trilobites molt repeatedly, shedding their rigid shells to accommodate expansion. Each molt leaves behind a perfect replica of the living body, preserved in astonishing detail. The accumulation of these molts across sediments explains the extraordinary abundance of trilobite fossils today. Each layer of rock becomes a library of growth, death, and transformation. Interactions between trilobites and other organisms deepen the structure of Cambrian ecosystems. Some species cluster around reefs, feeding on organic debris trapped among sponges. Others traverse open plains, leaving trails that cross worm burrows and microbial patches. Occasionally their tracks intersect those of predators, recording encounters frozen in stone. The abundance of trilobite remains in certain layers, hints at mass molting events or seasonal gatherings, possibly triggered by environmental cycles. Whether these behaviors reflect instinct or environment, they suggest coordination on scales larger than individual survival. The chemical record mirrors their rise. Calcium carbonate deposition increases in parallel with the proliferation of shelled organisms, suggesting that the biological use of minerals is reshaping ocean chemistry. As trilobites and other arthropods build exoskeletons, they draw down calcium from seawater, influencing saturation levels and promoting further precipitation of limestone. The ocean becomes a vast feedback loop where biology and geology interact continuously. Shells alter chemistry, chemistry supports shells. Life and environment intertwine in mutual reinforcement. With time, trilobites spread into nearly every marine habitat. Their fossils appear in rocks deposited from tidal flats to deep slopes, indicating adaptability unmatched by most other Cambrian animals. Some species grow large, exceeding 30 centimeters in length, while others remain minute. Their morphology continues to diversify, producing elaborate spines, horns, and complex facial sutures. These features help distinguish lineages that will persist into later periods before eventually disappearing. Yet during the Cambrian they symbolize success, the embodiment of an evolutionary principle that favors flexibility through structure. In the broader tapestry of life, the rise of trilobites marks a new equilibrium between complexity and stability. Their bodies represent both innovation and standardization, a modular design that evolution can modify endlessly without losing coherence. Through them, the ocean gains not just movement, but choreography, an ordered dynamism that defines the character of Cambrian life. The seafloor, once a flat and featureless expanse, now crawls with articulated forms whose shells catch the filtered light like scattered fragments of armor. Above them drift the early predators. Beneath them, the worms and burrowers continue their slow work. The Cambrian Sea has reached a state of full animation. Life is no longer emerging. It is flourishing, layered and intricate, its pulse carried by the armoured travellers that march tirelessly across the ancient ocean floor. Beneath the calm surface of Cambrian seas lies a parallel world of softness and transience, a world that rarely fossilizes but once thrived in vast abundance. Among the sands and muds beyond the reefs live creatures without shells, without mineralized skeletons, their bodies composed only of tissue and membrane. These delicate forms make up the unseen majority of life, their presence known mainly through rare moments of perfect preservation. When conditions align, when fine sediment buries an organism quickly in oxygen. Pour water, the imprint of its body endures as a shadow of carbon and clay. From these impressions emerge some of the most extraordinary fossils on Earth windows into the hidden diversity that defined the Cambrian ecosystem. In certain exceptional sites, the secrets of this soft-bodied realm remain frozen in stone. The Burgess Shale of what is now Canada and the Chengjiang deposits of China preserve animals in exquisite detail, their outlines, appendages, and even internal organs visible as faint patterns of organic film. These Lagerstätten capture a snapshot of entire communities, swimmers, crawlers, filter feeders, and predators that together reveal the full complexity of the Cambrian biosphere. Each fossil represents not just an organism, but a vanished moment of motion, a worm twisting in the sediment, a swimmer collapsing as mud envelops it, a scavenger resting for the last time on the seafloor. Among the most striking inhabitants of this hidden world are the Lobopodians, worm-like creatures with soft, flexible limbs. Their bodies are segmented, but their legs end in tiny claws rather than jointed exoskeletons. They crawl across microbial mats, feeding on detritus or preying upon smaller animals. Some, like hallucigenia, carry spines along their backs thin as needles that deter predators in a sea increasingly filled with danger. Others, such as Achaea, display stubby limbs suited for clinging to sponges and reef surfaces. These early Lobopodians form a bridge between the soft-bodied worms of earlier ages and the arthropods that will dominate later ones. Their anatomy captures evolution in transition, an intermediate experiment in structure and movement. Other forms are even stranger. Opabinia swims with 5 eyes set atop a flexible head, its long trunk-like proboscis ending in a grasping claw. It moves with slow undulations, directing food toward a circular mouth positioned beneath the head. Though alien to modern perception, its design is consistent with the logic of adaptation. Multiple visual inputs to detect movement in dim light, a flexible feeding organ for reaching into sediment crevices, and a streamlined body for maneuvering through calm water. In the same deposits appear creatures like Nectocaris with fins, and a siphon suggesting propulsion by jet and Wiwaxia covered in soft scales and curved spines that shimmered faintly as it grazed the seafloor. Each species occupies its own ecological niche, combining simplicity of tissue with sophistication of form. The conditions that allow such preservation are rare and fleeting. The Burgess Shale formed at the base of a steep underwater slope, where periodic mud flows buried organisms in fine sediment that excluded oxygen. Without oxygen, decay slowed, and mineral films replicated the soft tissues before they disintegrated. Over time, the organic matter was replaced by thin layers of carbon, preserving even the outlines of eyes and gills. In Chengjiang, similar processes occurred within a subtropical sea along the margin of Gondwana. Fine volcanic ash and silt settled gently, capturing the impressions of animals before they could decompose. These events, though catastrophic for the creatures themselves, created records that outlast entire mountain ranges. The fossils from these sites reveal that the Cambrian explosion was not merely an increase in hard parts, but a burst of biological experimentation. Body plans diverged widely, some familiar, others entirely unique. Early arthropods developed limbs of extraordinary variation, from paddle-like swimmers to grasping appendages. Worms evolved feeding structures ranging from simple proboscides to elaborate jaws. Even the first chordate-like animals appear here, faintly tracing the lineage that will lead to vertebrates. The diversity of forms suggests that evolutionary space was newly open, that environmental stability and oxygen availability allowed rapid exploration of possible anatomies. In these soft-bodied communities, interactions are complex yet delicate. Predators like Anomalocaris hunt among clusters of smaller organisms, while scavengers glide over the remains of the fallen. Filter feeders anchor themselves to sponges or microbial mats, extending tentacles into gentle currents. The seafloor becomes a mosaic of microhabitats, burrows, crevices, algal films, each supporting species adapted to its texture and chemistry. Some organisms live symbiotically, their bodies harboring photosynthetic or bacterial partners that provide nourishment. Others drift as plankton, living brief lives suspended between light and darkness. Every surface, every patch of sediment is occupied by life in some form. Despite their abundance in life, few of these creatures survive in the fossil record. Most vanish without trace, their bodies dissolving within hours of death. Only under exceptional conditions does their story persist. Yet through these fragments, a picture emerges of a world far richer and more intricate than once imagined. The soft-bodied animals, though fragile, drive much of the ecosystem's energy flow. They graze microbial mats, recycle organic debris, and provide prey for larger predators. They are the connective tissue of Cambrian ecology, the invisible scaffolding beneath the visible shells. The Burgess and Chengjiang faunas also demonstrate that complex sensory and behavioral systems already exist at this early stage. Many species show evidence of eyes, gills, and muscles arranged for controlled movement. Some possess paired appendages capable of coordination, suggesting nervous systems sophisticated enough for pattern and rhythm. The emergence of such structures implies not only anatomy, but the beginnings of ecology driven by perception organisms responding dynamically to one another in real time. The Cambrian Ocean, once an arena of simple feeding and growth, becomes a web of interactions based on awareness and choice. Geochemical traces within these deposits further illustrate the interplay between biology and environment. Iron and sulfur levels indicate alternating phases of oxygenation and stagnation cycles that may have influenced evolutionary pressures. During oxygen-rich intervals, predators and active swimmers flourish. During hypoxic phases, burrowers and microbes dominate. The waxing and waning of these conditions over millions of years shape the patterns of diversity visible in the fossil record. Life adapts continuously to chemistry, just as chemistry responds to life. Soft-bodied fossils bridge the unseen with the enduring. They reveal that the apparent simplicity of Cambrian life hides layers of complexity invisible in ordinary rock. Without them, the record would be skewed toward the armoured and the durable, giving the illusion that early life was dominated by shells. In truth, the majority of creatures were delicate and transient, their existence sustained by balance rather than strength. Through rare preservation, these lost forms speak again, showing that fragility itself was a successful strategy in a world newly filled with oxygen and opportunity. As the Cambrian progresses, many of these lineages will vanish, leaving behind only descendants in altered guise. But for a brief geological moment, the seas are alive with soft forms, ribbon-like swimmers, spined grazers, transparent drifters, all moving in the dim light beneath the waves. Their lives are ephemeral, their traces faint, yet their collective impact profound. They embody the creative abundance of evolution's first flowering, a quiet multitude whose memory survives only in the thin dark layers of shale that once sealed them from decay. Beneath the weight of eons, their shadows endure silent evidence that the dawn of animal life was not armoured but soft, luminous and brief. The equilibrium of the Cambrian Ocean begins to shift. For hundreds of millions of years, life has gathered energy passively from sunlight, from dissolved chemicals, from organic matter drifting through water. Now a new interaction spreads through the food web. Living creatures begin to feed upon one another. This change marks the rise of predation, a biological innovation that transforms every aspect of the marine world. The sea that was once filled with slow grazers and quiet filter feeders becomes a dynamic arena of movement, strategy, and response. Eyes sharpen, limbs grow stronger, and armor hardens as evolution adapts to a new form of pressure, the struggle between hunter and prey. Predation is not an isolated event, but the culmination of multiple developments already underway. The rise of oxygen allows larger bodies to maintain high metabolic rates. The spread of hard parts provides both protection and structure for muscle attachment. The diversification of sensory systems, light-sensitive patches, antennae, cilia, and chemical receptors makes detection possible. With these tools, life crosses an invisible threshold from reaction to pursuit. The first predators are not necessarily large. Even a small worm capable of active hunting represents a profound shift. Each predatory act introduces feedback into evolution. Prey that survive pass on traits for speed, armor, or awareness, while predators evolve sharper senses and more efficient movement. The fossil record captures this escalation in subtle traces. In early Cambrian sediments, the marks of simple grazing give way to deeper burrows, escape traces, and repaired injuries on shells. Drill holes in small fossils hint at attacks by specialized borers. Jagged edges on Trilobyte exoskeletons show that even heavily armored creatures are no longer safe. Over time, the variety of defensive structures multiplies: spines, plates enrollment mechanisms, and camouflaged bodies. Predation reshapes anatomy, behavior, and ecology simultaneously, turning the sea into an ever-evolving field of adaptation. Among the most formidable of these early hunters is Anomalocaris, a swimmer several tens of centimeters long, large enough to dominate its environment. Its body tapers to a flexible tail fan, propelling it with graceful efficiency. At its front, two grasping appendages studded with spines sweep prey toward a circular mouth lined with serrated plates. Its eyes, composed of thousands of lenses, detect motion from afar, giving it a sensory advantage over slower creatures. To its prey, Anomalocaris represents an unprecedented danger, a mobile visual hunter capable of active pursuit. Yet its success also accelerates innovation among those it hunts. Trilobites develop thicker shells and the ability to roll tightly for protection. Burrowing behaviors become deeper and more complex. The dance of adaptation begins, each advance met with a countermeasure. Smaller predators proliferate alongside their giant counterparts. Free-swimming worms evolve grasping jaws made of hardened cuticle, enabling them to capture plankton or small benthic animals. Some develop proboscides tipped with teeth extending into sediment to extract hidden prey. Others hunt cooperatively in swarms, overwhelming defenses by sheer numbers. These interactions are recorded not in the bodies themselves but in the sediments. They disturb trails of pursuit, patterns of avoidance, and concentrations of broken shells. The seafloor becomes an archive of motion, its texture written by the constant interplay of attack and escape. Vision becomes central to this new ecology. Before the Cambrian light primarily guided photosynthesis and orientation, now it guides behavior. The evolution of image-forming eyes allows animals to detect shapes, distance, and movement with precision. This ability transforms the ocean into a visual environment where color, contrast, and motion carry meaning. Even simple forms of perception, light versus dark, direction of shadow, enable effective predation and evasion. The seas grow brighter with evolutionary possibility. Creatures that see are no longer limited to responding after contact. They can anticipate, plan, and choose. the biological world becomes aware of itself. The consequences extend beyond behavior. Predation influences population structure and community composition. No longer can a single species dominate indefinitely. Predators prevent overgrowth, maintaining ecological balance. This dynamic fosters diversity as prey adapt in multiple directions, some toward mobility, others toward armor or chemical defense. The result is an increase in complexity that ripples through the entire ecosystem. The Cambrian Explosion is not merely a proliferation of forms, but an escalation of interaction driven by the energy flow from hunter to prey. Evidence of these changes appears in the sedimentary record as patterns of distribution and abundance. In layers corresponding to predator-rich intervals, fossils of fragile organisms decline, replaced by those with sturdier shells or burrowing habits. The vertical structure of communities deepens as more animals take refuge within the substrate, creating a three-dimensional ecosystem from surface to sediment. Burrows become longer and branch, some showing evidence of repeated occupation, a sign that life has learned to hide as well as to move. Predation also enhances biogeochemical cycles. The shredding of organic material by hunters increases the availability of nutrients, feeding microbial decomposition and recycling carbon through the water column. The constant turnover of biomass accelerates chemical exchange between organisms and their environment. The ocean's oxygen budget responds in kind as more animals respire oxygen. Demand rises, prompting further evolution in circulation and metabolism. In this way, predation connects biology to global chemistry, linking individual encounters to planetary processes. The evolution of active locomotion complements this shift. Fins, flaps, and segmented appendages enable more efficient propulsion. Swimming becomes not just possible but purposeful. Creatures traverse larger territories, linking previously isolated ecosystems. Energy moves through space more rapidly, carrying the effects of predation beyond local habitats. Even planktonic communities feel the influence as predatory larvae and juvenile stages drift among them. The entire marine realm becomes interconnected by motion, its stability dependent on balance between pursuit and renewal. In this changing world, fear becomes as significant a force as hunger. Prey species evolve behaviors that minimize risk: nocturnal activity in deeper water, rapid burial in sediment, or association with protective structures like reefs. Some develop sensory hairs or pressure receptors to detect approaching movement. Others rely on transparency, reducing their visibility in the water column. These innovations mark the beginning of behavioral ecology, where survival depends not only on physical form but on timing awareness and response. The rise of predation redefines evolution itself. Natural selection now acts through interaction rather than environment alone. Adaptations become relational teeth matched to shells, speed matched to camouflage vision matched to darkness. The Cambrian Sea becomes a crucible of arms races, each lineage influencing the fate of others. The result is not chaos but complexity, a web of feedbacks that will persist through all subsequent eras. By the end of the Cambrian, this new ecological order has stabilized. Predators remain relatively few but decisive, shaping the diversity and distribution of life across the planet. The oceans hum with continuous activity, swimmers gliding through filtered light burrowers, reshaping mud, and grazers scraping microbial films under the watchful gaze of hunters. The stillness that once defined Earth's early seas has been replaced by motion, purposeful, responsive, and unending. The rise of predation transforms the ocean from a passive environment into a living field of awareness where every movement carries consequence. In that transformation lies one of life's most enduring revolutions, the moment when survival becomes a contest and evolution begins to see itself through the eyes of the hunter. Within the vibrant waters of the Cambrian, amid trilobites, worms, and soft-bodied grazers, appear creatures whose forms seem modest, yet hold immense consequence. These are the first chordates, the earliest members of a lineage that will eventually lead to fish, amphibians, reptiles, birds, and mammals. Their emergence represents a subtle but decisive transformation, the development of a supporting rod within the body, known as the notochord, and a central nerve cord running above it. This innovation gives structure to movement, strength to flexibility, and the foundation for a new way of living. Though small and fragile, the earliest chordates introduce a design capable of refinement through deep time, one that will define the future architecture of complex life. The fossils of these pioneers are rare and delicate. In the Chengjiang deposits of southern China, one finds Pikaia, a Millikan-Mingia creatures only a few centimeters long, preserved as faint impressions of muscle bands and tissue. Their bodies are slender and bilaterally symmetrical, with a head distinct from the trunk and a tail fin used for propulsion. Along the midline runs the notochord, a flexible rod of cells, enclosed by a sheath that provides both support and motion. Muscles on either side attach to this rod, contracting alternately to produce graceful undulations. This simple arrangement and internal axis of strength, combined with paired muscles, marks a radical advance in anatomy. It allows movement independent of rigid armour and opens the path toward active swimming in open water. Unlike the arthropods with their jointed exoskeletons or the mollusks with their shells, these early chordates rely on an internal framework. The lack of heavy external armour makes them light and agile, but also vulnerable. To compensate, they depend on speed manoeuvrability and perhaps coordinated sensory responses. Their heads bear small eyes or light-sensitive patches, and at the front of the mouth fine gill slits filter water for oxygen and food. These slits, supported by cartilage-like rods, later evolve into gill arches and eventually in far future forms into jaws. In the Cambrian Sea, however, they serve a simpler purpose, breathing and feeding combined into one efficient flow. Water enters through the mouth, passes over the slits and exits behind the head, leaving oxygen for respiration and microscopic particles for nutrition. The same system that sustains the body also propels evolution forward. The chordates are not alone in exploring this new mode of structure. Other related lineages, such as the hemichordates and early cephalochordates, share aspects of the same plan. Together they form a family of designs experimenting with internal symmetry, segmented musculature and controlled motion. Some burrow through sediment using peristaltic waves, others swim freely through the water column. The distinction between these lifestyles illustrates the expanding range of ecological strategies emerging at this time. Life is learning to occupy not just the seafloor but the space above it, to move efficiently through water rather than merely across or within it. The appearance of chordates signals a shift from surface-bound existence to three-dimensional navigation. Their streamlined forms tapered at both ends minimize drag. Their tails act as rudders, providing thrust and stability. The arrangement of muscle blocks or myomeres along the body enables fine control of movement. This combination of internal structure and external shape introduces an entirely new level of mechanical precision to animal life. It allows sustained swimming rather than short bursts and makes migration across distances possible. The oceans, once divided into layers of floating and bottom-dwelling creatures, now host active swimmers moving freely between realms. Chemical evidence supports this transition. Carbon isotopes in Cambrian strata indicate increased organic turnover, a sign of more active respiration. Fossils of early chordates appear alongside those of predators, suggesting that both groups drive one another's evolution. Agile swimmers require oxygen and energy. Hunters and prey alike refine their physiology to sustain activity. The result is an acceleration of metabolism across the biosphere. The emergence of backbones coincides with the ocean's growing dynamism, a convergence of structure and environment that propels evolution forward. Within the anatomy of Pikaia and Milocunmingia lie the seeds of complexity unseen in previous organisms. The dorsal nerve cord protected within the body forms a primitive central nervous system. It coordinates movement through electrical signals, allowing precise control over muscles. The presence of paired sense organs indicates bilateral symmetry, not just in form, but in perception. These developments suggest a shift from simple reflexes to integrated response, where information from the environment shapes motion in real time. Even without true brains, these animals exhibit the architecture of intelligence in potential. The water column itself becomes the theatre for their expansion. Free-swimming chordates exploit niches that stationary or bottom-dwelling creatures cannot. They feed on plankton, small particles, or suspended detritus, filtering it through gill slits, or capturing it with gentle suction. Their speed enables them to avoid sluggish predators and to seek food over larger territories. In time, this freedom of movement will give rise to active hunters, but in the Cambrian it simply marks a new equilibrium life in motion, sustained by internal design. The preservation of these forms in fine-grained mudstone provides a glimpse into their delicate structure. The faint outlines of Myomere's gill supports and notochords reveal an elegance of proportion that belies their simplicity. Unlike the heavy exoskeletons of Trilobites, these creatures leave behind only ghostly impressions, dark films of carbon on pale rock. Yet within those shadows lie the foundations of every vertebrate to come. From these fragile bodies will descend the armoured fish of the Ordovician, the amphibians that crawl onto land, and the mammals that breathe air beneath future skies. The Cambrian chordates are the first whisper of that lineage, the opening line of a story that will continue through all of Earth's later ages. Their emergence also alters the fabric of the marine ecosystem. As they move through the water, they transport nutrients vertically, linking surface and depth. Their waste feeds benthic microbes, which in turn recycle material back to the photic zone. This circulation enriches both the chemical and biological structure of the sea. The interaction between free-swimming chordates and the rest of the biosphere strengthens feedback loops that stabilize oxygen and carbon cycles. In this sense, even these minute swimmers contribute to planetary regulation, connecting metabolism to climate. Comparing these early chordates to their contemporaries highlights a shift in evolutionary strategy. Trilobites and arthropods' perfect external form, chordates' perfect internal coherence. The first relies on building outward defences, the second builds inward systems. One defends against environment, the other adapts to it through agility. Both succeed, yet their futures diverge. The arthropods will dominate diversity while the chordates will dominate scale. The emergence of the backbone, humble and flexible, proves more transformative than any armour. It is a structure not of resistance but of coordination, a line of balance through which motion flows. By the end of the Cambrian, chordates remain few, their fossils rare, their forms small. But their influence is disproportionate to their numbers. They represent a new kind of organism that uses inner architecture to master external space. Their descendants will refine this design until it becomes the vertebral column, encasing nerves, muscles, and organs in a framework of bone. For now they glide through ancient seas, silent and quick, the first creatures with bodies shaped from within. Their motion is the quiet prototype of all future motion, a blending of symmetry, structure, and intent. In their fragile shadows lies the blueprint of the living world, to come a promise written softly into the sediment of the Cambrian Ocean, where the first backbones flex beneath the pale light of an ancient sun. Beneath shells, membranes, and soft translucent skins, the anatomy of the Cambrian world begins to reveal its intricacy. Life is no longer defined merely by outward form. It is now structured within. Organisms that once relied on simple diffusion for energy and respiration develop networks of internal systems that distribute, circulate, and coordinate. The quiet revolution unfolding inside these bodies parallels the external diversification seen in reefs and ecosystems. In this invisible realm of tissue and fluid evolution, experiments with muscles, guts, nerves, and vessels, the internal machinery that will define the future of animal life. At the most basic level, the Cambrian body becomes compartmentalized. Layers of cells specialize into tissues with distinct roles. Outer layers protect and sense. Middle layers move, inner layers digest and circulate. These divisions permit efficiency and complexity. In worms and early arthropods, sheets of muscle wrap around the body in bands, contracting rhythmically to generate propulsion. The muscle fibers themselves grow more organized, anchored to internal septa or external plates, converting chemical energy into motion. With this refinement, creatures no longer drift aimlessly. They can crawl, burrow, or swim with purpose, their movement directed by coordination between tissue and nerve. Digestion evolves from simple absorption to a process of mechanical and chemical breakdown. In the earliest multicellular animals, nutrients entered the body by diffusion through the skin or by engulfment of small particles. By the Cambrian digestive tract stretched through the length of the body, lined with specialized cells that secrete enzymes and absorb nutrients. This internalization of feeding transforms metabolism. Food can be stored, processed gradually, and distributed through the organism. A through gut with separate mouth and anus appears, allowing continuous intake and output, a small but revolutionary improvement that increases energy efficiency and supports higher activity. The evolution of gut cavities marks a shift toward internal autonomy. Each organism becomes a self-contained system capable of sustaining complex behavior. Circulatory structures emerge in tandem with these digestive advances. Thin networks of vessels or channels carry nutrients and gases between tissues. In soft-bodied worms and arthropods, these networks form open systems where blood or hemolymph flows freely through cavities. In others, primitive hearts develop muscular tubes that contract rhythmically, pushing fluid through the body. This movement distributes oxygen and removes waste, linking all organs into a coordinated whole. The chemistry of blood varies across groups. Some use copper-based pigments, others iron, but the principle remains constant. Internal circulation replaces reliance on diffusion. With it, size and speed become feasible. The Cambrian Ocean begins to fill with organisms large enough and active enough to need internal plumbing. Respiration follows a similar trajectory of specialization. Many small creatures continue to breathe through their skin, but larger forms require dedicated structures. Gills evolve as folds of tissue that increase surface area for gas exchange. Water passes over these folds, releasing oxygen into blood vessels beneath. In trilobites, fine filaments line the legs, each a miniature organ of exchange. In chordates, gill slits open along the pharynx, drawing oxygen-rich water through the mouth and expelling it behind the head. The emergence of respiratory structures demonstrates life's adaptation to both the opportunities and the limitations of oxygen. The atmosphere may now contain enough to support active metabolism, but only organisms that can deliver it efficiently to tissues can fully exploit that potential. The nervous system also undergoes profound expansion. Early animals possessed simple nets of nerve cells that transmitted signals without central coordination. By the Cambrian, those nets condense into cords and ganglia concentrating control. Arthropods develop ventral nerve cords running the length of the body, each segment with its own cluster of neurons to regulate movement. Chordates form a dorsal nerve cord protected by tissue and fluid. The result is an internal communication network capable of integrating sensation and action. Reflexes become faster movement, more precise. Sensory structures diversify as well. Simple eyes detect brightness and shape. Antennae and hairs perceive vibration and chemical gradients. The internal body is now linked to external reality through organized perception, creating a feedback loop between stimulus and motion that will define the behavior of all future animals. Reproduction and development reflect the same internal logic of specialization. Eggs contain stored nutrients to sustain embryos during early growth, and protective membranes evolve to prevent desiccation or damage. In many Cambrian organisms, fertilization occurs externally with gametes released into the water, but the formation of gonads and ducts indicates increasing control over reproduction. Within microscopic egg cells divide and differentiate into tissues according to inherited patterns. The emergence of embryonic layering ectoderm, mesoderm, endoderm sets the template for all future anatomy. These layers correspond to surface muscle and gut, establishing a structural language that evolution will repeat endlessly across new species. Excretion. Another internal process becomes more refined. Instead of releasing waste directly through cell surfaces, animals evolve nephridia tubular organs that filter fluids and excrete soluble byproducts. This innovation helps regulate the internal environment, maintaining balance of salts and water. The Cambrian body for the first time maintains homeostasis, a stable internal chemistry, independent of the outside world. With it comes resilience to fluctuation and an ability to inhabit a wider range of environments. Microscopic examination of Cambrian fossils reveals hints of these systems. In cross-section, dark traces of digestive tracts, faint lines, where nerve cords once ran clusters of organic carbon, marking hearts or glands. Each imprint represents a new level of biological organization. No longer are organisms merely collections of cells. They are integrated systems of organs performing complementary functions. This organization makes complexity self-sustaining. Energy intake, circulation and response no longer depend on external stability. They are managed internally by feedback mechanisms that anticipate and correct imbalance. Life has turned inward to sustain its expansion outward. The chemistry of tissues reflects this transformation. Collagen fibers, a protein that provides strength and flexibility, appear widely among Cambrian animals. Its production requires oxygen linking molecular evolution to atmospheric change. Collagen binds cells into sheets and layers, forming the scaffolding of muscles, skin, and connective tissue. Its resilience allows soft-bodied creatures to grow larger without collapse. The emergence of such molecular structures demonstrates that evolution operates not only at visible scales, but at the microscopic level where chemistry becomes anatomy. From these internal systems arise patterns of coordination that hint at future possibilities. Rhythmic contractions of heart and gut synchronize with muscular movement. Neural circuits produce oscillations that control swimming or crawling. Behavior emerges as a function of internal timing, not mere reaction to external cues. The Cambrian body has become a machine that organizes itself in time as well as space. This self-regulation pulse-breath motion marks the transition from simple living matter to organismal integration. Though few of these systems fossilize completely, their indirect evidence fills the Cambrian record with new signatures. greater diversity of trace fossils, thicker shells supported by muscle, increased carbon isotopic variation from respiration. The seafloor sediments reveal the outcome even when the organs themselves are gone. Every burrow, every track, every feeding trail represents not just a behavioral act, but the function of muscles, nerves, and guts working together. The landscape of the ocean floor becomes an anatomical imprint enlarged to planetary scale. By the end of the Cambrian, internal complexity has spread through every major lineage. Arthropods refine circulatory and nervous systems. Chordates develop organized musculature. Worms and mollusk precursors establish efficient digestive and reproductive patterns. Each group carries forward the same fundamental plan: separation of internal spaces coordination through nerves and maintenance of stable chemistry. What began as a microscopic experiment in tissue differentiation now defines the architecture of life itself. The seas teem with organisms that not only move, but feel, feed, breathe, and regulate. Inside each translucent body flows an unseen choreography of fluids and signals, an orchestra of chemistry and motion that sustains existence. In the quiet depth of the Cambrian Ocean, the interior of life has awakened. Within those fragile bodies, invisible to the light above, the blueprint of all future anatomy has already taken shape. Across the Cambrian world, the ocean becomes a laboratory of mineralization. For the first time in Earth's history, life begins to incorporate stone into flesh, transforming soluble elements of seawater into armor scaffolding and architecture. The chemistry of hard parts, shells, spicules, plates, and exoskeletons marks one of the most decisive evolutionary transitions ever to occur. What begins as microscopic crystal formation soon reshapes the balance of power in the sea, altering the carbon cycle, ocean chemistry, and the very texture of sediments. Through biomineralization, life and geology fuse into a single system. Biology writes itself into stone. The seawater of the Cambrian provides the perfect medium for this transformation. It is saturated with calcium carbonate, phosphate, and silica, all dissolved by weathering of the young continents. When organisms begin to regulate these minerals internally, they unlock new structural possibilities. Calcium carbonate, formed from calcium ions and carbonate in seawater, precipitates easily within living tissue. It appears first as tiny plates or granules that strengthen the surface of cells or tubes. Over time, these crystals coalesce into continuous shells, exoskeletons, and frameworks. The chemistry of life and the chemistry of the sea align in a single process of construction. Two main materials dominate these early hard parts: calcium carbonate and silica. Calcium carbonate forms the skeletons of trilobites, mollusk-like creatures, and reef builders such as archaeochiathids. It can crystallize in different forms, calcite or aragonite, depending on temperature, pressure, and seawater composition. Silica, derived from the weathering of continental rocks and volcanic ash, forms the spicules of sponges and the protective coats of small plankton. In each case, the mineral serves both protection and support, allowing organisms to grow larger and more complex. Once life begins to build with minerals, evolution accelerates strength, enables mobility, protection, enables exposure, and structure enables specialization. The process of biomineralization is both biochemical and physical. Within cells, specialized proteins and membranes control where and how crystals form. Organic templates guide mineral nucleation, ensuring that crystals align in specific orientations. Layers of organic and inorganic material alternate, creating composite structures stronger than either component alone. In trilobite exoskeletons, for instance, a thin organic matrix binds calcite prisms into a tough, flexible armor that resists compression while allowing movement at segment boundaries. This interplay of mineral rigidity and biological elasticity is the key to the success of shelled life. The appearance of hard parts also transforms ecology. For predators, mineralized teeth, claws, and spines make capture and consumption more effective. For prey, shells and carapaces provide defense-forcing new strategies of attack. This feedback loop drives an evolutionary arms race that shapes Cambrian biodiversity. The oceans become a mosaic of armored grazers, spined swimmers, and burrowing escape artists. The chemistry of minerals thus underlies the physics of survival. It defines not only who lives and who dies, but also how entire ecosystems organize themselves. The sedimentary record reveals this shift with clarity. Before the Cambrian, most seafloor deposits consist of fine muds and microbial mats. After mineralization spreads, carbonate sands and skeletal debris dominate. Broken shells accumulate to form coquinas and limestones. Fine particles of biogenic calcite rain down to fill basins with chalky sediment. The rate of sedimentation increases, and the composition of the ocean floor changes permanently. Geology and biology are now interdependent. Living organisms generate the very sediments that preserve their remains. Chemical evidence from ancient seawater trapped in fluid inclusions shows that the concentration of calcium and carbonate fluctuates through the Cambrian, reflecting biological uptake. As more organisms build shells, they draw down calcium from the ocean, reducing saturation levels and stabilizing carbon dioxide in solid form. This process links evolution to climate regulation. Carbon, once dissolved in seawater or released as volcanic gas, becomes locked in limestone, cooling the planet slightly, and establishing a feedback system that will operate for hundreds of millions of years. Each shell, each skeletal fragment participates in this planetary balancing act. Silica-based skeletons follow a different chemistry. Unlike calcium carbonate, silica is less readily precipitated under normal conditions, requiring biological mediation. Sponges achieve this through proteins known as silicatins, which catalyze the formation of glass-like spicules inside their bodies. These microscopic rods and needles reinforce their form while maintaining flexibility. The transparent skeleton allows light to penetrate, supporting symbiotic microbes within their tissues. The emergence of silica use introduces variety into the architecture of hard parts, ensuring that evolution explores multiple mineral pathways simultaneously. Phosphate also plays a minor but significant role. In certain small shelly fossils such as halkyrids and tomatids, calcium phosphate forms protective scales and tubes. Phosphate is more resistant to dissolution than carbonate, giving these structures remarkable durability in the fossil record. Their presence demonstrates that early organisms experimented with available minerals, testing which chemistries best suited different needs. The Cambrian Ocean, rich in chemical options, becomes a proving ground for biological innovation. The spread of biomineralization has consequences beyond individual organisms. It changes how sunlight interacts with the ocean, increasing reflection and altering temperature gradients. It modifies the alkalinity of seawater, influencing the solubility of gases. It even affects the trace metal composition of sediments as iron and magnesium become incorporated into shells. Through these processes, life reshapes the planet's geochemical cycles, introducing a biological layer to global regulation. From this point forward, the history of Earth cannot be separated from the chemistry of living matter. Inside each mineralized body, the relationship between organic and inorganic material defines the identity of the organism. Shells provide scaffolding for muscle attachment, allowing stronger motion. Joints evolve where plates meet, giving rise to mechanical precision. The rigidity of skeletons supports the development of complex sensory organs by providing stable frameworks for eyes and antennae. Even the evolution of nervous systems benefits from the structural stability that hard parts afford. The entire trajectory of animal design becomes interwoven with mineral chemistry, yet the adoption of hard parts also brings cost. To build with calcium carbonate or silica organisms must expend energy and maintain chemical control. Excessive acidity in the water can dissolve shells, and mineral deposition requires regulation of ion balance. These constraints make shell-building species sensitive to environmental change, binding their fate to ocean chemistry. Periods of rapid weathering or volcanic activity alter seawater composition, forcing evolutionary turnover. In this way, biomineralization becomes both a gift and a risk, a powerful adaptation that increases potential, but ties life more closely to Earth's shifting geochemical state. By the end of the Cambrian, the transformation is complete. The seafloor gleams with fragments of mineralized life from trilobite carapaces to the tiny scales of shelled microfauna. Reefs of limestone rise where sponges and archaeocyathids once filtered water. Every current carries suspended grains of biogenic material, turning the ocean into a realm of living rock. The boundary between organism and environment has blurred. Calcium that once drifted freely in seawater now forms the architecture of life itself. In the silent rhythm of waves and sediment, the chemistry of hard parts has bound biology to geology forever. The ocean no longer merely supports life, it is built by it, grain by grain, crystal by crystal, in the slow, enduring alchemy of the Cambrian Sea. Within the rocks of the Cambrian, the story of life becomes written at scales invisible to the naked eye. Beneath the smooth surfaces of limestone and shale lies an archive of textures, crystals, fibers, and microscopic patterns that record how biology and chemistry intertwined in ancient seas. These microstructures reveal details that ordinary fossils cannot: the architecture of shells, the layering of sediments, the rhythmic growth of organisms responding to light season and nutrient flow. The ocean of the Cambrian is long vanished, but its memory survives in these fine details where stone and cell once met. The smallest fossils of this age are the so-called small shelly fossils, a diverse collection of minute plate tubes and spines measuring only millimeters across. Under magnification, their surfaces display intricate ornamentation, ridges, pores, and lattices that once strengthened delicate structures or filtered water. Many belong to organisms whose complete forms remain unknown: transitional species that experimented with mineralization in countless ways. Their shells often consist of alternating layers of crystal and organic material, each layer only micrometers thick. The precision of these laminations reveals that early Cambrian life possessed remarkable biochemical control, capable of shaping minerals into complex geometries through organic templates. The result is both functional and aesthetic, a natural engineering that fuses structure with pattern. When viewed in cross-section, the microtextures of these shells show rhythmic banding, each band reflecting changes in environmental conditions. Variations in oxygen salinity or temperature leave distinct mineral signatures. Some layers grow rapidly, marked by coarse crystal grains, while others form slowly, producing smooth, translucent bands. These cycles are the pulse of ancient oceans, preserved in stone seasonal records written by living matter. Through modern analysis, scientists can infer the length of Cambrian days, the stability of climates, and the chemistry of seawater, all encoded in these microscopic strata. Every growth line becomes a calendar of deep time. Even the larger fossils such as trilobites and archaeocyathids preserve microstructural details that speak of the physiology behind their form. The Trilobite exoskeleton, composed of calcite prisms oriented with optical precision, shows interference patterns under polarized light, a sign that evolution had already discovered the physics of light manipulation. The prisms act as miniature lenses within the eyes, allowing vision through solid crystal, while other layers provide strength without brittleness. This fusion of function and chemistry anticipates the structural materials of modern engineering, but was achieved by cells operating under the slow guidance of evolution. Sedimentary rocks from Cambrian seas likewise reveal microtextures that record environmental motion. Thin sections of limestone show cross-cutting laminae where storms stirred the seabed, mixing shells and mud. Microscopic ripples in shale preserve the flow of gentle currents across microbial mats. In some cases, entire bacterial communities are fossilized as films of carbon, their filaments intertwined like threads in fabric. These microbial layers trapped sediment and built stromatolitic domes, whose cross-sections display fine internal lamination, each sheet a day or week of growth. In the still waters of tidal flats, such mats were as ubiquitous as grasses in a modern meadow, creating living surfaces that mediated between water and rock. Microfossils also capture the earlier stages of animal reproduction. Tiny eggs and embryos only a fraction of a millimeter wide appear in phosphatized nodules from ancient sediments. Their cell divisions are frozen mid-process, revealing the same patterns of cleavage seen in modern marine animals. The preservation of these microscopic lives speaks to the mineral richness of Cambrian seas and the rapid burial that protected them. In these fossils, the origin of multicellular development is recorded not in theory, but in tangible geometry spheres within spheres, each dividing according to inherited code. Chemical microanalysis further enriches this record. Isotopic ratios of carbon and oxygen in shell layers indicate the composition of seawater, while trace elements such as strontium and magnesium mark variations in temperature. Iron and sulfur isotopes in pyrite nodules reveal the extent of anoxia on the seafloor. These data form a continuous geochemical diary, allowing modern researchers to reconstruct the changing balance of oxygen, carbon dioxide, and nutrients across the Cambrian world. Beneath the broad story of evolution lies this subtler narrative of chemistry, in which life and environment record one another in reciprocal detail. In certain fine-grained shales such as those of the Burgess and Chengjiang formations, the preservation of soft tissue reaches cellular resolution. Carbon films reveal muscle fibers, gut linings, and even neural cords, their microscopic structure outlined by minerals that replace decaying tissue molecule by molecule. Under electron microscopes, these patterns resemble modern biological ultrastructure, bundles of filaments, vesicles, and membranes captured at the instant of transformation. The fidelity of this preservation is extraordinary. Ancient protoplasm, converted into stone yet retaining the geometry of life. The boundaries between living and mineral matter blur entirely. These microstructures also illuminate the processes of fossilization itself. When an organism dies in the Cambrian Sea, its decay releases organic acids and ions that interact with surrounding sediment. Phosphates precipitate, replacing soft tissue. Iron sulfides form in anoxic microenvironments, preserving outlines. Clays encase delicate forms in protective films. The result is a spectrum of preservation that varies with depth, chemistry, and microbial activity. Every fossil, even a microscopic one, is both a biological and a geochemical artifact, a collaboration between death and environment. The study of Cambrian microstructures extends beyond biology into the philosophy of time. Under magnification, each polished slice of rock becomes a window into billions of individual events, crystal growth, cellular secretion, the settling of dust. What appears smooth to the eye is at microscopic scale chaotic with detail, each layer a frozen moment of motion. The beauty of these patterns lies in their precision. The order of their arrangement speaks of repetition governed by natural law. The fine cross-laminations as mudstone, the radiating prisms of calcite, the spiraled shells of microscopic mollusks, all record the physics of a world where chemistry and life had only just found equilibrium. These details also reveal continuity between past and present. Modern shells, corals and bones display the same microtextures as their Cambrian ancestors, the same crystalline lattices, the same organic scaffolds, the same layered rhythms of growth. Evolution has refined but not reinvented this architecture. The tools life devised 500 million years ago remain effective today. Each tooth, each scale, each coral branch echoes a Cambrian blueprint. The smallest structures in ancient stone thus bridge the gulf of time, showing that life's fundamental chemistry was established early and has endured almost unchanged. At larger scale, the cumulative effect of these microstructures shapes the Earth's crust. Over millions of years, the accumulation of shell skeletons and microbial films creates strata kilometers thick. When these rocks later fold into mountains, the microscopic laminae align into marble and schist, preserving faint ghosts of their original texture. Even metamorphosed, the rhythm of ancient life persists within them as trace alignments of mineral grains. The mountains that rise long after the Cambrian still carry at their core the structure of its seas. In the end, the Cambrian record in stone is more than a collection of fossils, it is a high-resolution map of process. Each grain, crystal and layer encodes an interaction between biology and physics, between growth and environment. What began as the invisible work of cells now defines the visible landscape of Earth. Through microstructure, the transient forms of living matter become permanent, surviving the loss of ocean and continent alike. The stone remembers not only the shapes of creatures, but the rhythms of their growth, the chemistry of their breath, and the pulse of the waters that carried them. In these minute patterns lies the continuity of the planet itself, a memory etched at molecular scale, whispering of a time when life first learned to leave its trace. As the Cambrian draws toward its close, the world that once pulsed with novelty begins to settle into stability. The explosive diversification that filled the oceans with strange forms slows, giving way to equilibrium. Ecosystems mature, competition balances, and extinction prunes the excess of experiments that marked the age's beginning. The Earth itself has changed beyond recognition from the world that entered this era. Its atmosphere holds more oxygen, its oceans are thick with calcium carbonate, and the remains of living matter and its continents are ringed with reefs, tidal flats and inland seas. The Cambrian does not end in sudden collapse, but in transformation, a quiet reorganization of life and environment into the foundation of all that follows. By this time, continents drift into new configurations. Gondwana dominates the southern hemisphere, immense and stable, while Laurentia Baltica and Siberia approach positions that will foreshadow the formation of future supercontinents. Shallow epicontinental seas still flood their margins, but gradual tectonic uplift and shifting climates cause periodic regressions that expose vast stretches of sediment to air. Each retreating sea leaves behind layers of limestone and shale, built from generations of marine life. These sediments are thick with trilobite fragments, worm burrows and faint microbial textures, a stratified memory of the Cambrian Ocean. With every advance and retreat of water, new environments arise, new communities adapt, and others disappear. The continents themselves now act as engines of biological change. The trilobites, so abundant through the Cambrian, continue to dominate the seafloor, but begin to face decline in certain regions. Fluctuations in oxygen and nutrient availability lead to localized extinctions, while new predators test the limits of their armor. Some species shrink, others develop spines or thicker shells. The variety of forms once increasing exponentially stabilizes. What remains are lineages refined for endurance rather than novelty. The trilobites' long reign will extend into the next era, but their greatest diversity belongs to the Cambrian, the time when their segmented bodies defined the rhythm of life on the seabed. Around them, simpler creatures continue their work, burrowing worms, filter-feeding sponges, and small arthropods that graze across microbial films. Together they form the enduring scaffolding of marine ecosystems, quiet and persistent. Predation, once a revolutionary pressure, now forms part of the normal rhythm of life. Hunters and prey have reached a kind of truce through adaptation. Armor speed and sensory systems have reached functional equilibrium. The great predators like Anomalocaris vanish, replaced by smaller, more efficient successors. The food webs they helped establish remain intact, their energy flow stabilized by diversity. The Cambrian world has learned the pattern of balance, the interplay of death and renewal that will sustain the biosphere for ages. It is in this balance that the first signs of long-term ecological resilience appear. Environmental change continues nonetheless. Periodic fluctuations in sea level, driven by tectonic movement and climatic variation, reshape coastlines and shallow basins. Each regression drains habitats, each transgression renews them with fresh sediment and nutrients. In these cycles lie both opportunity and loss. The shallows so crucial to Cambrian life are fragile zones easily disturbed by shifting chemistry. Episodes of anoxia periodically sweep through deeper waters, suffocating benthic organisms and altering the pattern of fossil deposition. These events, though, regional, foreshadow the mass extinctions that will punctuate later eras. Yet recovery always follows. The biosphere of the late Cambrian proves remarkably robust. Its diversity ensures that no single failure leads to collapse. Chemically, the ocean continues to evolve. As shells and skeletons accumulate on the seabed, they sequester calcium and carbon dioxide, gradually reducing greenhouse gases in the atmosphere. The Earth cools slightly, and polar regions begin to host seasonal ice. Ocean currents strengthen, enhancing oxygen distribution. The balance between biological productivity and chemical deposition becomes a global regulator. For the first time, the biosphere exerts measurable control over the planet's climate. The Cambrian marks not only the origin of animals, but also the beginning of life's governance over planetary processes. From this point onward, biology will influence geology as profoundly as geology shapes biology. In the fossil record, the final chapters of the Cambrian appear as alternating bands of dark shale and light limestone signatures of fluctuating oxygen and carbon cycles. Within these layers, certain faunas vanish abruptly. Trilobite families disappear from some continents. Reef communities collapse and reappear elsewhere. The causes remain debated: changes in sea level nutrient limitation or shifts in ocean circulation, but the result is clear: extinction resets the evolutionary field. The survivors inherit an ocean already structured, already oxygenated, and already chemically stable. They will carry forward the Cambrian legacy into the Ordovician, where new groups, brachiopods, echinoderms, and early vertebrates will rise to prominence. The microbial world, largely overshadowed, in the record of visible animals, continues its silent dominion. Cyanobacteria still generate oxygen and build stromatolitic mats in protected shallows. Microbes colonize sediments, reefs, and even the shells of animals, mediating chemical exchange between living and dead matter. Their unseen activity maintains the equilibrium of the sea recycling elements that might otherwise be lost. The Cambrian explosion may have introduced animals, but microbial life remains the planet's sustaining engine. Beneath the visible drama of evolution, it continues without interruption. As the Cambrian fades the sediments, it leaves behind become the framework of geological memory. Limestones compact into marble shales transform into slate, yet within them the fine laminae of ancient seas persist. The fossils they contain, eyes of calcite, spines of silica. Impressions of soft tissue become the vocabulary through which future ages will read the dawn of complex life. These rocks are not merely remains, they are a record of process and archive of the planet's awakening. Each layer is both a moment and a continuum, the sum of countless lives reduced to patterns of mineral and void. Viewed from the long perspective of deep time, the Cambrian appears brief, a single bright surge in Earth's 4 billion year history. Yet its impact is permanent. Every animal that follows inherits its innovations, the body plans, organ systems, skeletons, and behaviours first tested in these seas. The neural networks of fish, the shells of mollusks, the segmented limbs of insects, and the vertebral columns of humans all trace back to this era of experimentation. The Cambrian established the rules by which evolution would proceed: differentiation, integration, and adaptation through interaction. Its legacy is not its creatures' strangeness, but their success in building the blueprint of multicellular life. By the end of this age, the oceans are no longer experimental laboratories, but structured realms of continuity. Ecosystems recover from disturbance, lineages persist across continents, and the interplay of chemistry and biology achieves lasting balance. The Earth that emerges from the Cambrian is self-regulating, oxygenated, and teeming with interconnected life. It has learned stability through diversity, resilience through structure. The storms that once swept through shallow seas now write rhythms rather than catastrophes. The Cambrian does not close with silence but with harmony, the first sustained equilibrium between life and planet. Long after the waves that shaped these ancient coasts have vanished, the rocks remain. Inside them lie the traces of a world both alien and familiar, a world that taught the planet how to live with itself. The waning Cambrian leaves not extinction but inheritance, a biosphere prepared for expansion, a climate moderated by life, and a memory preserved in stone. In those memories lie the roots of all that follows: the coral reefs of the Ordovician, the forests of the Devonian, the vertebrates that will walk on land. The Cambrian ocean withdraws, but its rhythm endures in every living thing.